Today, then, we are going to talk about capacitive comb drives. So I'm going to attempt to draw something, and I'm going to pre-apologize for it looking like the hottest of garbage. So this is going to be effectively just a portion of a microstructure. And what I am attempting to draw are long, skinny fingers of a three-dimensional structure. Imagine that these lines were straight. So this is going to be some stationary portion. And I'm going to attempt to 3Dify this thing real quick. Like so. And then down here, I'm going to draw some more fingers. Once again, trying not to make this look like garbage, but probably being unsuccessful. Okay, and let's just say for what it's worth that these fingers right here are capable of moving. Now, they could possibly move in several different directions, and we'll talk about all of those cases and how that would wind up impacting the performance of a device. Before we go ahead and do that, let's identify a couple of critical things here, okay? So first, let's look between here and here. This is a distance that I am going to call D2. Okay. And then the distance between this finger right here and one of these side fingers, actually, is what I'm going to call a distance D1. And there is the exact same distance D1 over on this side. So what I am attempting to illustrate here is that because we have some gap D1 between our stationary plate and our movable plates, we should form some capacitances. So I'm going to put a capacitance here that I'm going to label C subscript SL. So the subscript S is for sidewall, and the subscript L is for left. So we have some capacitance formed between the side walls of those interdigitated fingers. We have one on the left, and we should see that there is an additional sidewall capacitance over here on the right that I'm going to call CSR, like so. Okay. And then there's going to be a capacitance formed between the end of one of our movable fingers and that back wall of our stationary structure. I'm going to call this one CF, which stands for a fringe capacitance. So typically speaking, let me write this down really quickly. Typically speaking, CSL and CSR are much, much greater than our fringing capacitance. The reason for this is twofold. One, the area of overlap of the end of one of the fingers is incredibly small, which means the area portion of the epsilon A over D bit of parallel plate capacitance is going to be small. Additionally, the distance there between the end of the finger and that back wall of the stationary bit is typically large as well. So these fringe capacitances are typically ignored. They do exist, and they are an example of a parasitic or unwanted capacitance in these systems. But for the most part, they're going to be so much smaller than our intentional sidewall capacitances that we are largely going to ignore them. Okay. All right, so let's talk about the multiple different cases that we might see, okay? So the first case that I want us to cover is going to be lateral movement. So I'm going to put a simplified version of kind of a top-down view of one of these guys really quickly, okay? So here's our basic structure, something like this, where we have an array of fingers. Like so. And then in between those fingers, we have additional interdigitated fingers. Like so. And these additional interdigitated fingers are connected to some form of anchor point. To define a simple coordinate system for this guy, the y direction is going to be up. The x direction will be to the right. And then the z direction will be out of the page. And let's say that in this case, our axis of motion is in the y direction, okay? So we are going to form sidewall capacitances, CSL, and CSR. We're going to neglect our fringe capacitance. And what's going to happen is as this top structure moves back and forth in the y direction, the area of overlap between the top structure and those fixed fingers is going to change, which in turn gives us some form of variable capacitance, right? So if we had an accelerometer or something based on this, if an acceleration caused that top structure to move, we could then measure that change in capacitance and relate it back to the amount of acceleration that our structure underwent, okay? So our capacitance CSL and our capacitance CSR are going to be exactly equal to each other, assuming that our interdigitated fingers are equally spaced apart. All of the other dimensions are the same, okay? So the value of these capacitances should simply be epsilon naught times what I'm going to call L naught plus Y times T naught over D naught. So let me define those dimensions really quickly. So L naught is our nominal overlap, right? So that's this dimension right here, right? So this is the rest state amount of overlap. And then as Y increases, meaning the area of overlap increases, we should see the overall capacitance go up. If Y were to decrease or be in the negative direction, the amount of overlap would decrease and the overall capacitance would go down. So everything so far seems to make sense. Our dimension D naught is just the distance between these fingers, right? That is not going to change. And then our dimension T naught is effectively the thickness of the fingers, right? So if this is a top view, then a side view representation would just be something as simple as this, where this dimension is T naught, and this coordinate system, this would be the Z dimension, this would be the X dimension, and into or out of the page would be the Y direction. Okay. So the total capacitance would simply be twice N, where this is simply the number of fingers, times CSL or CSR, right? So the number of fingers is fairly obvious. The factor of 2 comes from the fact that every finger is going to have a corresponding capacitance on the left and the right. So this comes out to be 2n epsilon naught L naught plus Y T naught over D naught. And we can define a displacement sensitivity. We'll call that S subscript Y. And so this is sensitivity to changing capacitance. And this is simply going to be the partial derivative of our total capacitance to Y, which in this case simply becomes 2n epsilon naught T naught over D naught. So this sensitivity effectively for simple structure like this tells us how much our capacitance is going to change for a particular displacement, right? So our change in capacitance, delta C, is just going to be our change in Y times SY. So we can see that the change in capacitance is proportional to the change in displacement, okay? Nothing particularly wild or crazy there. So realistically, if we cause a movement that causes the area of the overlap to increase by 10%, the capacitance then increases by 10%. Nothing particularly wild or crazy there. Yes.
Just how not is that the length that is inside that area of capacitance, or that's just the area of
So that is the rest position length of the overlap. So if this system is at rest, there is no acceleration or anything like that being underwent, then it is by how much the fingers overlap before they experience any perturbation to the system. So the total amount of overlap is then L naught plus Y, where Y represents that change. Is that okay? All right, so there's our first case. Any other questions about this guy? Nothing too terribly wild or anything. Okay. So our second case that I want us to look at then is vertical movement. So in this particular case, we go back to our original figure. We are allowing those movable fingers, excuse me, to move up and down, right? So instead of moving in and out of the gap, they're moving up and down. And so what we would see if we looked at a kind of side view thing would be something like this. So we would have one finger, and for what it's worth, we'll say this is our stationary finger. And then over here, and this is kind of a dashed line kind of silhouette thing. We have our other finger, and this dimension right here, Z, is going to be the amount of displacement that is experienced by our fingers, right? We're going to call this distance right here L naught. So that's the amount of overlap of the two fingers. In this case, it is not going to change. Here is our thickness, T naught, right? And both fingers should nominally have the same thickness in a structure like this. And then just defining a simple coordinate system. Here's our z-axis. Our x-axis is out of the page. Here's our y direction. So we've got a fairly similar situation to what we saw earlier. The area of overlap is what's changing here, right? So our sidewall capacitances CSL and CSR are once again going to be equal to each other because the gap between the fingers isn't the thing that's changing. And so we can just apply our simple parallel plate capacitor formula, epsilon A over D. So epsilon naught, our area is just, our area of overlap here, excuse me, is just our length L naught multiplied by our thickness T naught minus Z, the amount of displacement our finger moved. And then all of this is divided by our nominal gap, D naught. That makes sense to everybody given everything. Oh, and just as a heads up, this is our axis of motion or movement or whatever you want to call it. Okay. Our total capacitance, C total, is 2N, where N once again is the number of fingers, times CSL. So this is 2N epsilon naught L naught T naught minus Z all over D naught. And our displacement sensitivity in the Z direction is the derivative of our total capacitance with respect to Z, and this is going to come out to negative 2N epsilon naught L naught over D naught. So once again, our displacement sensitivity is effectively just a constant, which means our total capacitance and any displacement we see are linearly related to each other, so that our change in capacitance is literally just a change in Z times SC. So nothing particularly wild or crazy here. It's literally just the exact same thing that we saw moving the fingers in or out. It's just the area that's changing is changed. So the third and final option that we have is transverse movement. So I'm going to redraw a structure here. So this is a top-down view. I don't like that color. Something like this. And let's say that we are allowing things to move in this direction. Where this is our Y direction, this is our Z, and this is our X. Let me go ahead and draw some fingers down here. So I'm going to draw it as if it had already experienced some movement, such that maybe this finger right here is very close to a finger, and it's also far away from the opposite finger. So that we would have a dimension here that we're going to call D naught minus X, and we're going to have a dimension here that we're going to call D naught plus X. Okay. Our amount of overlap, L naught is this dimension, and then T naught is going to be our finger thickness as it was previously. Okay. So this is the only case that we're going to deal with where our left sidewall capacitance and our right sidewall capacitance are different from each other, right? So what we should see is that CSL, our left sidewall capacitance, is just going to be a parallel plate capacitor, so epsilon A over D. So epsilon naught, our area is simply our length L naught times our thickness T naught. And in this case, our distance D is D naught minus X. And similarly, our right sidewall capacitance will be epsilon naught L naught times T naught over D naught plus X. Right? So for n number of finger pairs, the total capacitance is going to be simply n times CSL plus CSR. Right? So this is going to come out to be n times epsilon naught L naught T naught multiplied by a factor of 1 over D naught plus X plus 1 over D naught minus X. And we can define our displacement sensitivity Sx as the derivative of our total capacitance with respect to changes in the X direction. And so this is going to be n epsilon naught L naught T naught times 1 over D naught minus X quantity squared minus 1 over D naught plus X quantity squared. And this is the only case where our change in capacitance is not equal to our change in displacement times our sensitivity, because we have a nonlinear relationship between displacement and capacitance, because it's the gap that's changing and not something in the numerator. So these are capacitive comb structures, very, very frequently used in devices like accelerometers. And we should be able to see from these three different examples how if we put three of these things integrated together, we could have a 3-axis accelerometer, right? Because we've talked about measuring a change in displacement in the X direction, a change in displacement in the Y direction, and a change in displacement in the Z direction. So 3 of these guys together with the springs stiff in particular directions to only allow movement in the X, Y, and Z direction gives us a 3-axis, accelerometer. All right, so how do you guys feel about Mr. Finch?
If you use 3 of them in the first place, why don't they just point into them in 3 different directions?
So for the X and Y, you could literally orient them perpendicular to each other. The Z is an entirely different movement. Right? So having these 3 different structures for X, Y, and Z, using them in the ways that I have described here, that would have been like how they first did it, but they've done things now to make things more efficient. So like you can do X and Y, for example, by literally just repeating the same structure and just changing the other one 90 degrees out of phase, as opposed to having it relate to an entirely different area changing mechanism or something like that. For the Z axis, it's more likely that you wouldn't. So if we look at this guy back here just really quickly, if we're looking at vertical movement, right? This is a possibility, but this is going to wind up creating the smallest signal because the area of overlap is so small kind of to begin with. We're going to see the smallest amount of change. So more realistically, it might make sense to have a large parallel plate over an electrode, and when that large plate moves, we see a large change in capacitance instead of a whole bunch of smaller plates with a smaller area moving to try to generate a similar signal. So, but these are just 3 different ways that we could get a change in displacement to a corresponding electrical signal. Okay. Any other questions about this stuff?
So you're saying these are using accelerometers. How would you extrude like the acceleration or like?
So when we talked about the capacitive sensing lecture in the previous lecture, that Wednesday before,
Yeah.
that's literally covering that. So how do you convert a change in capacitance into an electrical signal? That's what we talked about before the break. Okay. All right, any other questions about this before we move on to the very beginning of, let's see, piezoresistive sensing? All right. So does anybody have a damn clue what the word piezoresistive means? Effectively, yes. So it's a resistance that changes under mechanical stress or mechanical strain. But effectively, if you want to call that strain a pressure, meaning you're pushing on it or something like that, perfectly reasonable. Okay. So piezoresistive sensing effectively uses what's known as the piezoresistive effect to convert some type of mechanical deformation into an electrical signal. Okay. So let's say that I have a simple beam structure. Okay. So this is what our beam looks like at rest without anything particularly done to it, okay? So I'm going to define this dimension as the length and this guy right here as our cross-sectional area A. Okay? So if we are assuming that current is flowing through this beam, the resistance of the beam, R, is given by rho E, which is the electrical resistivity, times the length of the beam divided by the cross-sectional area. I believe I've used this relationship before when we were talking about the electrical review stuff, right? So if I were to force this beam to undergo some form of mechanical deformation, so let's say that I tried to stretch it out, what we should see is that the cross-sectional area technically gets smaller. As this beam extends. Where these dashed lines are representing effectively what we see after mechanical deformation. And this is caused by some stress in the x direction. Okay. So what we are going to do is we are going to define what's called a fractional change in resistance. And that's going to be a ratio of the change in resistance divided by effectively the nominal resistance. And this is going to be given by the change in resistivity over resistivity minus the change in area over the nominal area plus the change in length over the nominal length. So our first term is effectively a change in the material, and then the last two terms are all about the change in the geometry, okay? So we are going to define a piezo-resistive coefficient. So our piezo-resistive coefficient is going to be pi, and pi is given by the change in resistivity over resistivity, so the fractional change in resistivity per unit stress, or delta rho E over rho E divided by Young's modulus times our strain. So this looks like a fairly straightforward relationship, except that most materials, particularly single crystalline silicon and things like that, are anisotropic, which means they are going to undergo different material changes in different directions. Okay? So another important figure of merit that is used to characterize the piezoresistive resistive effect is the gauge factor, and this is defined as the fractional change in resistance per unit strain. So our gauge factor, GAUGE, will be GF is equal to delta R over R divided by delta L over L, or 1 minus the change in area over delta L over delta L, or 1 plus twice Poisson's ratio plus E times our piezoresistive coefficient. So this is just effectively our fractional change in resistance relationship expressed in a slightly different form, where these guys right here are from our geometric effects, and this guy right here is from our material properties. Similarly, up here, we had material, and over here we had geometry. So just kind of a slightly skewed way of looking at things. So speaking about gauge factors, we can write a little table here. So material will be on the left, gauge factor will be on the right. And we're going to talk about, oops, I can't spell aluminum today. Aluminum. So the gauge factor for aluminum, which is used in CMOS processes, 1.4. Copper, 2.1. Platinum, 2.6. Nickel is negative 12.62. So notice that nickel has a gauge factor whose magnitude is much, much larger than other metals we might see. For this reason, nickel is what's commonly used in macroscopic strain gauges, right? So for those of you guys that did your engineering stuff or your undergraduate engineering stuff here and probably dealt with strain gauges in your statics class, chances are they were literally just chunks of nickel with electrodes connected to them. And as that nickel deformed, the resistance changed, and that's what gave you the electrical signal that you were using to figure out how much your change was, okay? For polycrystalline silicon, gauge factor can range anywhere from -30 to +40, which means does a very good job of translating deformation into electrical signal because it's got a large gauge factor. And then single crystalline silicon is even better, -102 to +135, dependent on crystal orientation and all of that kind of good stuff. Okay. So let's talk specifically now about the piezoresistive properties of silicon. So for single crystalline silicon in the 100 family of planes, the relationship between resistivity and stress can be expressed using the following matrix. So we're going to have delta rho 1 over rho naught. Then here is delta rho 2 over rho naught, delta rho 3 over rho naught, delta rho 4 over rho naught, delta rho 5 over rho naught, and lastly down here, delta rho 6 over rho naught. And I will definitely talk about what all these mean here in a moment. So this is our fractional change in resistivity. And here we're going to have a matrix of piezoresistive coefficients. Okay. So here we're going to have pi 1, 1, then pi 1, 2, pi 1, 3, and then 0, 0, and 0. Pi 1, 2, pi 1, 1, pi 1, 2. Actually, sorry, I made a mistake. This one right here should have been 1, 2 as well. So just to recap things really quickly, pi 1, 1, the piezoresistive coefficient in a particular direction is running along the diagonal. All of the other guys are pi 1, 2, and then the right-hand side of everything is 0. Jumping slightly ahead, we would have stress T1, T2, and T3. And these are essentially what we've been calling to this point TXX, TYY, and TZZ, which are simply normal stresses in the X, Y, and Z directions. All right, continuing along our piezoresistive coefficient matrix, now we're going to have 0, 0, 0, and then pi 4, 4, 0, 0, 0, 0, 0, 0, pi 4, 4, 0, and lastly 0, 0, 0, 0, 0, pi 4, 4. So effectively now we've got those pi 4, 4 in the diagonal Howdy. This is going to be stress T4, 5, and 6. And these are corresponding to shear stresses. TYZ, TXZ, and TXY. So we can see essentially that we have different piezo-resistive coefficients depending on whether or not we are applying a normal stress or a shear stress, and then depending also on the directions that we are applying those stresses in, okay? So we have 3 independent piezo-resistive coefficients for silicon, pi 1,1, pi 1,2, and pi 4,4. These coefficients are not necessarily constant because they depend on doping concentration, doping type, and temperature. So generally speaking, sorry. I'm going to put pi ij here in this table. So this is going to tell us which one we're looking at. And typically speaking, the units for these coefficients are 10 to the minus 11 inverse pascals. And then for over here, we're going to do N-type silicon, which has an electrical resistivity of 11.7 ohm centimeters, or at least that's what we're going to be using in this class because that's what I have in my table. And then P-type will have a resistivity of 7.8 ohm centimeters. And these values are at 300K for the number of acceptor atoms, Na, or the number of donor atoms, Nd, is less than 10 to the 17 atoms per cubic centimeter. So this would be standard N-type and P-type, but not N plus or P plus. So it's not heavily doped materials. Okay. So what you might see in a normal bit of semiconductor material, doped semiconductor material that isn't being used for like an implant or something like that, which has a very, very high conductivity because it's very heavily doped. So this is kind of like raw wafer material that's pre-doped for us. So pi 1,1 has a value of negative 102.2 for N-type and positive 6.6 for P-type. Pi 1,2 has a value of 53.4 for N-type and negative 1.1 for P-type. And lastly, pi 4,4 is negative 13.6 for N-type and 138.1 for P-type. So these are the pi ij values for piezo-resistive coefficients we'll use for single crystal and silicon. Okay. So when strains occur in directions other than the 1, 0, 0 direction, so strictly the X, Y, and Z directions, that requires us to use different combinations of anisotropic piezo-resistive coefficients. So we've got yet another table coming at you, and this is, I think, where we're going to wind up stopping for today. Okay. So let's put direction of strain here. The direction of how our current is passing through here. Our configuration here. And then our piezoresistive coefficient here. All right, so let's say that we're looking at a strain in the 100 direction and current going in the same direction. This would be a longitudinal configuration. So they're in the same direction and current's just flowing down the length of the bar. Here we would simply use the coefficient pi11. Okay. Now, if our direction of strain is 100 and our direction of current is, let's say, 010, effectively all this means is that they're 90 degrees or perpendicular to each other. Now we have a transverse configuration. And we would use pi12. If we have a strain along the 111 crystal plane, sorry, the 110 crystal plane, and our current is also flowing in the 110 plane, we would have longitudinal, and our piezoresistive coefficient is going to be 1/2 pi11 plus pi12 plus pi44. We have 110, and then our current is flowing at 1 -10. So once again, just perpendicular. We have a transverse configuration, and it's going to be the exact same coefficient, except that we're going to flip the sign on the last term. And then lastly, for a 111 direction strain and a 111 direction current, our coefficient is going to be 1/2 pi11 plus twice pi12 plus twice pi44. Let me move this line over. All right. I think this is a good stopping point for today, and we only have a minute left of class anyway. Sorry for the 15-ish minutes of me forgetting my notebook and then technical delays of trying to find a classroom where the projector actually fucking worked. So, thank you for your time. See you on Wednesday. I swear to God, at some point, you're actually going to get homework assignments in this class.